A proton is traveling in the positive x direction in an unknown magnetic field, and it experiences a magnetic force in the positive y direction. On the other hand, an electron is traveling in the negative z direction in the same unknown magnetic field, and the electron also experiences a magnetic force in the positive y direction. Now, we'd like to find this unknown magnetic field. What are the magnitude and direction of this unknown magnetic field? Now, if we apply the right-hand rule to the proton's velocity is in the positive x direction and the magnetic force is in the positive y direction. Now, if you align your right hand in the direction of the proton's velocity in the positive x direction, if your thumb is pointing up in the direction of the force, your fingers are curling into the page, that is negative z direction. So that means the magnetic field is in the negative z direction, right? Or it could be a magnetic field that has many components, multiple components, and the component that creates the magnetic force that is affecting the proton is in the negative z direction. So that's like the z component of the magnetic field. On the other hand, let's apply the right hand rule to the electron, aligning our right hand in the direction of the electron's velocity into the page or into the screen, and our thumb is pointing up, our fingers are curling in the negative x direction, right? But that's for if the particle was a positively charged particle. This is an electron, so we flip the direction. So that means the direction of the magnetic field is in the positive x direction. So that's the component of this unknown magnetic field that is creating the force on the electron, right? And this component is not able to create any force on the proton because both the velocity of the proton and this component are in the x direction. Whereas the component that is affecting the proton, which is in the negative z direction, cannot have any effect on the electron because the electron is also moving along the z-axis in the negative z direction, basically. So then again, the protons, the force acting on the proton tells us about the z component of the unknown magnetic field, and it points in the negative z direction. And the force acting on the electron tells us about the x component of the unknown magnetic field, and this one is in the positive x direction. Let's set up our formula to find the z component of the magnetic field. We use the magnetic force formula for the proton. So the magnetic force acting on the proton is equal to the proton's charge times its speed times the absolute value of the magnetic field z component. Note that I'm keeping everything positive because this is not a vector equation. This is just the formula for the magnitude of the magnetic force acting on the proton. We already know that b sub z is pointing in the negative z direction, so we know that here we're just calculating the absolute value of b sub z. We rearrange our equation to isolate b sub z and then plug in the numbers. Keeping two significant figures, I get b sub z absolute value is equal to 1.1 Tesla. Next, we go through the same calculations for the electron. This time we're looking for the absolute value of the x component of the magnetic field, and we know that the x component is pointing in the positive x direction. We set up the force equation, definition of the magnetic force, isolate the x component of the magnetic field, and then plug in the numbers. Keeping two significant figures, we get 1.0 Tesla. Now let's combine these two to find the magnitude and direction of the overall magnetic field vector. To find the magnitude of the magnetic field, we apply the Pythagorean theorem. Here we only have x component and z component. We don't have a y component, so the magnitude is equal to the square of the x component of the magnetic field plus the square of its z component, and then we take the square root. So B equals 1.5 Tesla. Next, let's find the direction angle of the magnetic field. Here's a sketch of the magnetic field vector. The magnetic field vector has x and z components only, so it lies in the xz plane. And I have the components listed here, the actual values, and z components, remember, is negative. So B points towards the negative z direction and the positive x direction. Let's find this angle right here. I'm going to call it angle alpha. We can find alpha by doing an inverse tan. Now let me draw a dashed line here. This is parallel to the z-axis. Here's a 90-degree angle. So this is a right triangle on the xz plane. The dashed line here is the opposite side of the angle alpha, and that's a z component, right? And this side right here is the x component, and it's adjacent to angle alpha. So then tangent alpha equals absolute value b sub z divided by b sub x. Why am I using absolute values? Because alpha is less than 90 degrees. So if you use negatives, then you may get wrong answers. When you're doing tangent alpha, always pick an angle that is less than 90 degrees, which is what I did here to calculate the direction angle, and use absolute values in your inverse tan calculation. After the numerical substitution, we get alpha equals 48 degrees, and that's 48 degrees from the positive x-axis towards the negative z-axis, like so. From the positive x-axis towards the negative z-axis. Now, given this magnetic field, if we have an electron moving in the negative y direction at 3.6 kilometers per second, what is the magnetic force acting on the electron? Let's just apply the magnetic force formula. This time we are given the vectors in component form, so we're going to do the cross product using the components. Here I have set up the formula for the magnetic force. Note that this is a vector equation. So for instance, when I substitute for the electron's charge, I use a negative number, right? So the force is equal to the electron's charge times V cross B. We are going to do a cross product using the components of the two vectors. Vector V has a y component only, so that's just j hat. And vector B has x and z components. Now first let's remember how cross product works with unit vectors. Here's a diagram showing the cross product rules for the unit vectors. So in this diagram, if you go in the clockwise direction, the result is positive. If you go in the counterclockwise direction, the result is negative. For instance, if you're doing I cross j, that's the clockwise direction, right? The result is just k hat. I mean I hat cross j hat, the result is k hat. If you're going in the opposite direction, if you're doing j hat cross I hat, which is in the counterclockwise direction, right, the result is negative k hat. Or if you're doing k hat cross product j hat, again I'm going in the reverse direction, right, the result would be negative I hat, etc. So in our cross product, what do we have? We have vector V that has only a y component, that's just j hat, and it's being multiplied by vector B, right, or V cross B. We are going to do a component by component multiplication. So for instance, we do the y component of vector V times the x component, or cross product the x component of vector B. That brings a j hat cross product I hat. Let me look at my diagram. If I go from j hat to I hat, that's counterclockwise direction. The result from here will be negative k hat. And the second term will be j hat cross product k hat. Again, let me go to my diagram. J hat cross k hat, that's in the clockwise direction. So the result will be positive I hat from that multiplication. So we'll have two terms from this cross product. And one is bringing up a factor of or a multiple of negative k hat, and the other one is positive I hat. So let's go ahead and do this calculation. And here's what we get when we do the numerical calculation. So the force vector acting on the electron at this moment is on the xz plane. It has a negative x component and a negative z component. Next, let's go ahead and find the magnitude of this vector and its direction angle. For the magnitude, again, we apply the Pythagorean theorem. Square the x component, square the z component, add them together and take the square root. We get 8.6 times 10 to negative 16 newtons. Now for the direction angle, I have my force vector shown on the sketch here. Again, it's on the xz plane, pointing in the negative x and negative z direction. So let me find this angle right here. I'm going to call it beta. So this is the angle from the negative x-axis towards the negative z-axis. How do I find this angle? Again, let me use inverse tan. Here's a dashed line parallel to the z-axis again. Here's a right triangle. So the z component is the opposite side and the x component is the adjacent side. Beta is equal to inverse tan of absolute value f sub z divided by f sub x. After the numerical calculation, we get beta equals 43 degrees. That's 43 degrees from the negative x-axis towards the negative z-axis.